I showed my wife some of these slides, and she was like, "At least you're not brutalizing them with math again." So this is ARM assembly from basics to party tricks. Of course, we could never get to advanced in 40 minutes. So I'm just going to show a couple of fun things that maybe you could take home with you. Okay. And so you might be saying, I don't really care about assembler. And all I got to say is I don't either, right? If everything worked, I understood everything perfectly, and my code ran fast, I would also not care about assembly. So basically, we've got to outline some sort of reasonable goal that we want to achieve here. And so my hope for you guys is that by the end of this, you'll be able to read 64-bit ARM assembler and then kind of leverage that understanding to see if the compiler is emitting the instructions that you want. So it's both read a little bit of assembler and also try and have a vision for what you think the compiler should be doing. And so what platform are we going to learn? I have an Apple Silicon machine, and so the code here isn't going to work anywhere else because assembly is not portable. It does turn out that it's not that big of a difference between any other ARM machine. So for instance, all the ideas here should transfer to a Raspberry Pi or an NVIDIA Jetson, Qualcomm Snapdragon. There's many, many, many more. And the main thing that you need to worry about is just syntactic changes for the assembler. Okay. All right, so I guess we're doing this. And so let's do the hello world, right? Hello world's too hard. Okay. So in assembly, the hello world, if you will, is exit code.s, and then we just return an integer return status. And that, I do believe, is the easiest program that we could write. Okay. And so here's a bit of code here. And so basically we say, I want a global symbol called main, and I want to byte align it to 4 bytes. And then I'm going to define my main. Okay. And then I'm going to move the number 7 into a 32-bit register. Okay. So in ARM assembly, all the 32-bit integer registers start with W. Okay, so W0 is the 0th 32-bit integer register. And then we're going to move number 1 into W16. Okay. And so one thing that you learn when you study assembler a bit is a lot of this stuff has to be done via agreements, right? We don't have like the notion of a function call. What we have is when this function hits that number, it is going to look in a certain register and it's going to expect certain data to be there. Okay? And so in this case, when we make this supervisor call, the supervisor call is going to say, let's look into W16 for what I'm supposed to do. And in this case, the number 1 means exit. And I'm going to look in register W0, the number for whatever's there, and I'm going to exit with that status. Okay. And so you can assemble this and link it and run it with the following syntax, and you can see when we execute it, we're going to echo that status, and it's going to give us a 7. Okay. So 64-bit ARM assembly has 64-bit registers as well. And so these are all labeled with the letter X. And so we could do the same thing here and do it in a 64-bit register. The high bits of these X registers are just the W registers. And this is an idiom that is probably familiar from doing x86 assembler as well. Okay, so now we can get to the hello world. And honestly, I don't find this to be a super compelling example. It's the same idea. You say, okay, I'm making agreements about registers. I'm saying, okay, like there's some agreement that when we put a 1 into X0, then it's going to be stood out. Okay. And then x1 is going to hold the address of our string, and x2 is going to hold the number of characters in that string. Okay, so it's still going about the same idea, which is in order to work in assembly, we have to really have agreements about register usage. Okay, and because these hello worlds are really, really challenging, we find printf debugging is like not so useful. Okay. And so what I like to do instead when I'm working in assembler is just assemble with symbols and use LLDB. And so here's a very basic thing. I apologize, that's not very big, but I put a breakpoint there and I run it. And then I can print the value of these registers, and that NI means next instruction. And I can go through and print the values of the registers one at a time, and then step through with this NI next instruction. So I actually think that the debug when you're writing assembly is actually easier than debug in C++ because you have less complete insanity between what you actually think is the fundamental representation of your code. But still using, stepping through instructions one at a time is not necessarily a lot of fun. Okay. Now, I think the most interesting thing about assembler is that when you're doing very fundamental things, turns out it's kind of easy. So here's the first thing, like if we want to add two integers, right? So what we're going to do is we're going to say, hey, let's start off by assigning a variable the value 7. And then I want to add 8 to it. Okay, this is actually not really a big problem, right? There's no ambiguity. Like, what is a long, right? Is a long 32 or 64, or is it an int, right? We just know right now we have a 64-bit integer register, and we're moving in that, and we're doing additions in that 64-bit register. And subtraction is easy as well. So we're just move a value into a register, and then we can do this sub s, and then at the end of this, x naught is going to be the difference between x2 and x1. Now this s at the end means set ALU flags, and so if you have studied computer architecture a little bit, you know that when some operation is performed, there are a number of flags you could set. For instance, you could set a carry flag, or a 0 flag, or an overflow flag. And so this particular instruction sets those flags. We actually don't use those in this particular example, but it's just representative. Okay? And then floating point is also pretty easy. You just prepend all the instructions that are floating point with f. So f move into D1, 7.5. F move into D2, 8.5, and then F add gets you to there. Okay. And then here we have another instruction, which is kind of, actually this instruction shows up on perf traces all the time. This is floating point convert towards 0 signed. So what this is doing is it's taking whatever floating point value is in D0 and then basically truncating it to the nearest integer. And this is actually a very expensive operation. So if you've ever seen like in C++, you'll see this as like static cast to int of some double, or round and static cast. Okay. So I want to study how the instructions are encoded, because this gives us a lot of insight into the ARM platform. Okay. And so the way that I like to study my my code is with LLVM object dump. There's another more classical tool called just object dump, and I think LLVM object dump is a little bit better. For instance, object dump will explicitly just like put stuff, like print integers in like little endian format, and you're like, oh, I've got to like rotate those in my head to figure out what the actual number is, right? Whereas LLVM object doesn't do that. And so for our exit code, when we dump it, you see Okay, the first instruction is at offset 0. Okay, and then the next one is at byte 4. And then the next instruction is at byte 8. Okay, and this is general for ARM. All the instructions are 32 bits. And so there are no instructions that are more than 32 bits. There are no instructions that are less than 32 bits. This is in contrast to Intel, where you can have variable length instructions. Okay. And so you see here, this is actually giving the opcode, well, the instruction in, hexadecimal here. Okay. And so naively, you might think you could get 4 billion instructions into that. But I have a question. Where, when we said move into X0, the number 7, where did that actually go? We didn't actually have like a data segment in this program. So this 7 is somewhere. Okay, so let's disassemble this other program. I've got another program that shows where this 7 went. Okay. So here we have a bunch of move instructions. Okay, and so I'm moving 0 into X0. And then I'm moving 1 into X0. I'm moving 2 into X0. And I'm moving 3 into X0. You can see along this column, this green here, it's actually doubling those numbers. Okay. So in hexadecimal, what is this indicating? Why is that doubling? Yes, it's actually starting, the immediate value actually starts at bit 5, not at bit 4. And so it's, you can see, okay, so this instruction is holding data at the same time. Okay. So we need the instruction. So when we had this, the one in our example, which we moved the number 7 into X0, that holds the data. Okay. And in ARM, you can hold any 16-bit immediate value. Okay, so an immediate is any number that is held in an instruction. So here's another example. Okay, so we have to encode the source and destination. Okay, so this one shows the source register changing and the destination register being fixed. And then you can see what changes in the instruction. Okay. And then this one shows which one the destination register. Okay. So you can see that we're losing a lot of bit patterns just to the need to tell what register things are in. Okay. And as an aside, I hope this we'll be able to like post this. I have some references on all the Arch64 bit patterns. Okay. And so here's an example of an Arch64 encoding. This is the move and negate instruction, and then this is the move and 0 instruction. Basically, like a move and 0 means clear all other bits that are not being used. Okay, and so what this says, the D is the destination, and then this I is all the immediate data. So this is 16 bits of immediate data. And then the X is what's called a don't care bit. So these bit patterns are not being used by the ARM standard. And then there's only 1, 2, 3, 4, 5, 6, 7 bits used for the opcode here. So the opcode is actually not that big, not a big fraction of the actual instruction. Okay. And so I have a quiz for you. Currently, Arch64 provides 32 integer registers, and they are labeled X0 to X31. Okay. Suppose the ARM designers decided that 64 registers would be better. What are the implications of that? Yeah. So the answer, I made this mistake last time. I didn't repeat the answer. I need to undo that. So the member of the audience said you will need an additional bit dedicated to that in the instruction. Okay, this is a calamity, right? You can't just like keep on running the same code when then the operations are meaning something different. So it's very, very difficult to add integer registers. Okay? There might be other ideas, right? So consider these two instructions, right? The first one is I'm going to move the value of the W1 register into the value of the W0 register. And then there's another instruction, which is a bitwise OR of WZR, W1, and then I'm going to move that result into W0. Okay? And so the WZR register is encoded as the 31st register. It's kind of like the dev null of registers. It always reads as 0 and it ignores writes. Okay? So you think these are clearly going to do the same thing, but when we disassemble them, it not only is going to do the same thing, it's the same opcode. And so the question is, where did this OR instruction go? And why are the opcodes identical? And the answer is that assembly is too high level. Okay. We have these notion of instruction aliases. Like if you optimize a circuit, okay, and you say, I've got my OR instruction, okay, and I really worked hard on it, right? Do I actually need to have a register move instruction? Well, I could just use my 0 register, right? I've got a 0 register, let's use it. So this is a very general principle. We want to reduce the number of operations that we actually need. And the 0 register, the dev null of registers, is there to help you. Okay. Yeah. Okay, so he said that it's going to be an idiom, and he's going to basically the superscalar architecture is going to actually like remap. He's going to find a 0 register, and it's going to just use that. Yeah. Okay. So one thing that I personally like to do is search around for custom instructions. Okay, things that a compiler might not necessarily generate. Okay, and so if you have a field of study, a subfield of study, learning about these things that have been implemented in hardware have extremely high return on investment. And so let's do a party trick. Okay, so there's a legendary algorithm from Quake. This is a very famous thing where they used basically a Newton iterate to get a reciprocal square root. And so if you have done work in computer graphics, you might know that a lot of your time is spent normalizing vectors, right? And so getting the normalizations quickly computed is very, very important for getting like a video game running. Okay? And so if you apply the Newton's method to this, did I lose? Oh, the bottom is an off button. I didn't, okay, sorry. Okay, so this is the Newton's method for this iteration. Okay? And so ARM actually provides this instruction called floating point reciprocal square root step. Okay? And it's kind of a strange instruction. So like you don't actually compute the Newton step, you compute this kind of sub-step, and you have to assemble the rest yourself. Okay. And so here is our assembler to actually do this. First thing I'm going to do is we're going to say, okay, D0, which is the double precision floating point register, is going to hold the value that we wish to check, to compute their reciprocal square root. And then our initial guess is a 1/1/2. Okay. And so then you square it, and then you do this floating point reciprocal square root step, and then you do another multiplication. Okay, and then you can do another iteration should you choose, and another iteration should you choose. Okay. And so we had a lot of duplication here. So let's see what we can do to reduce it. Okay, so here we do an iteration count, which we're holding in the X1 register, and we have a label here just called iteration. And we do the same thing. We just do the same sort of Newton iterate here, And then the whole control of this iteration just goes like this. You just add 1 to the integer register, and then you compare it to 5. And if it's not equal, we're going to branch back to iteration. And the next thing you might want to do is like actually make it a function. Okay? But to make things a function, you have to look up the ARM procedure call standard. So the procedure call standard is basically something where you go, hey, we're going to make an agreement. We're all going to agree what happens. Like, where is the first integer argument to a function? Where is that? Okay, we say, we're going to make an agreement. The first integer argument to a function is going to be an x0. What about the second? It's going to be an x1. What about the first double precision argument to a function? That's going to be in d0. So we got to go through and study these standards. And then we also have to figure out basically the callee saved and callee corruptible registers. Okay. So here we have a implementation of this r square root as a function. And so when we do this, the first thing we do, we have the first floating point argument to this function is just in D0. Okay. And then we use this branch and update the link register, that is BL. Okay. And so BL says branch this label and then update the link record. And basically, when you update the link record, you tell return where to go. Okay. And so basically what that's going to do is it's going to say, when I call read, I'm going to go to the next instruction after this BL. Okay. And so read is going to go to this move. After we go for the read, we're going to go to the move. Okay. And so how does this function know where to return to? It seems to just do the right thing in this point, but it basically puts the address of the next instruction, the program counter +4, in the x30 register. So this is another part of the just things you have to know, right? And so if you call read without any arguments, basically that always means return to x30, which is the program counter +4 before you call that. Okay. And so if you're actually insane, you can just return to any number in any register, but most of the time it'll just segfault. Okay. And so here's the next quiz, which is, why is this an infinite loop? Okay. Yep. So just said it. Register 30 is corrupted by the BL. Okay, so what happens first? I call branch with link record to bar. Branch with link record goes to the bar, and x30 points to right after that in main. Okay, then I call foo, and then the branch with link record goes to here, right? But then when it returns, it's going to go to right here. But then read from bar is actually going to go back to this no-op. And this is going to back. So basically the value in the procedure link register just got clobbered. Okay. So we need to figure out some mechanism to actually store that procedure link register. Okay. And so the first thing that you can do is you can use what's called the callee saved register. Okay. And so I could say, okay, I'm just going to copy the value in x30 into x24, and then I can return to x24, and then it's going to be okay, because foo is corrupting that x30. But this is kind of like not great, right? Because bar itself should save x24 because it's a callee saved, it's a function, and it's being called by somebody else. So the better fix is to actually push the link record to the stack. Okay? And so what we're doing here is we're going to store x30 to the stack pointer, and then we're going to actually decrement the stack pointer by 16, call foo, and then we're going to pop the stack. Okay. So you might notice x30 is a 64-bit register, and we're actually adjusting the stack by 16 bytes, okay, in this particular example. So why did we do that? We only really needed to adjust the stack by 8 bytes. Okay. And so in Arch64, you basically have to keep the stack 16-byte aligned. The assembler won't actually reject it if you do this, but then you get a bus error. Okay. And so the better question to me is like, why did ARM say that we have to have 16-byte alignment? And I found a blog post where one of the ARM designers was like, yeah, nobody knows. And so I think that this is kind of a deep thing, but you can go into the ARM architecture reference guide and it says, actually it can be configurable. You can make a choice as to whether you want the stack to be 16-byte aligned and terminate with a bus error. So at least on Apple Silicon, they did make that choice. So if you're not 16-byte aligned on the stack, there you go. Yeah.
There's a register called SP. Is that one of the X registers, or is it a special thing?
That's the stack pointer. I can't remember if it's X29 or X28. I can actually get that up in LLDB, because actually if you do a command in LLDB, it's called reg read. It will show you all the registers, and they'll be in order numerically, but they will have their aliases labeled. Pretty sure it's X29. I'm not going to check that right now because I'm only sharing my deck set. But okay. So if you have to adjust the stack by 16 bytes per operation, you might as well store 16 bytes per operation. Right? And so when you are reading assembly for ARM, you often see this STP instruction, which I read as store packed. It means put both X0 and X1 onto the stack. Then adjust the stack by 16. And then load packed, which means take both values off at once. So you just do both of these things in a single instruction. Yeah. So the exclamation mark, that means change it after you do this. Okay, so this is actually, there's, sorry, I did not read this for people online. The question is, what does the exclamation mark mean? There are what's called addressing modes in ARM. There's 5 that I know about. Okay, so one is post-indexed notation. That is the one on the bottom. So this reads SP, and then at the end, add 16 to it. And then this is pre-indexed, which is subtract 16 from the stack pointer, and then that's the value you get, and then also subtract, that's SP minus equals 16. So there's pre-indexed, post-index, and then you can also do, you can like do addressing modes to like labels as well. So that's in curse form. Yeah. The square brackets, that is pre-indexed notation. Yeah. Okay. So let's go back to this function call that we did, where we're doing a comparison instruction. Okay, so we did add 1 to each thing, and then we're saying, I want to do 5 iterations of this, and I'm going to compare that value to 5. Okay. If you disassemble this with -m no aliases, you will see this kind of strange thing, which is that the compare instruction actually becomes a subtract with set flags, and then write it to that kind of dev null register. So why did this happen? Well, ARM has what they call a strong risk heritage, right? They want to make sure to use the same instructions as many times as they can. Okay. And so anything that ends with an S means set flags. And so if you're going to do a subtraction anyway, you can actually refactor this loop to save an instruction. So instead of starting off with 0 and then counting up, we're going to start off with however many instruction counts we want, and then we just count down. Okay? And so you'll actually, if you run Godbolt very often, you'll see this idiom for doing loop iterations. Okay. Okay. And so conditional branching instructions can be read with the current program status register. And it's read in LLDB with the command reg read CPSR. And so I should probably also note that the ARM standard actually says this doesn't exist in 64-bit ARM, but like that's what LLDB still has. And so there it goes. Yes. I mean, I would just write it however it's natural and just let the compiler do its thing. But it's kind of confusing to read the assembler. You're like, wait, I said for I equals 0, I less than 5, do this, right? And then it starts off with 5. You're like, what? Where should my source code be associated to it, right? And so this is just a thing to keep an eye out for. Yeah. Okay, so yeah, I was trying to figure out how to summarize. I couldn't. I was like, it was a plea. Yeah. Okay, so the R square root that we just did was kind of didactic, and so I kind of want to do a good one here. And so here's one where we only use 3 registers and 5 instructions. And so the first, there's kind of a new instruction here, which is floating point reciprocal square root estimate. Okay? And so in the previous one, we said, okay, I'm going to estimate that the square root of 1 over the square root of 2 is about 0.5 as our first iteration. But it turns out ARM gives you something. This will give you like 2 digits of accuracy for D0. And then we use this Newton iterate to actually bootstrap that up to like 4 digits of accuracy. Okay. And so just because you have fewer instructions doesn't mean that you have better performance. Instructions can have different latencies. They are recorded in this link that I have provided, but they do seem to indicate that this is a very fast R square root. ARM tries to have most instructions complete in a single cycle. It's not always possible. That's kind of a dream, but they achieve it pretty regularly. Okay, so I actually have, I wrote some code for this, and I decided to actually benchmark these R square roots. So this is your naive R square root, where you do a F square root and an F div. And on an M2, I got that to iterate in about 0.9 nanoseconds. And so then I tried my single Newton iterate with the floating point reciprocal estimate, and it was actually 293 picoseconds. So very few performance benchmarks are reported in picoseconds, but I think it's fair. I'm not even go away, Max. I'm not gonna dignify that with a response. Not here. Okay, so if you want to incorporate stuff in C++, the way that you do it is extern C. You can just link it right in. It's actually pretty simple if you're staying on a single platform. And if you guys are interested, there's another floating point reciprocal, basically just estimate the reciprocal. So there's the same thing for division here. So if you ever need to make a division go fast, there's 2 instructions that do the same thing. Okay. And so you might say, I'm not a graphics programmer and I don't care about R square root. Okay. But if you type this into your Mac, then you can find other interesting hardware instructions. Okay. And so if you're into crypto, hey, there's a hardware instruction for SHA-256, 512, AES, polynomial multiplication over a Galois field, and then random number generators. Okay. What if you're into cybersecurity? You can do pointer authentication and like restrict speculation. Okay, and maybe you're into JavaScript, and so there's actually custom instructions for JavaScript. Okay, and if you're into machine learning, you can do, there's hardware instructions for half precision numbers, hardware dot products, matrix multiplication, and so these are the sorts of things that you would want to attack. Should you really want to get into these sorts of topics and really study hard and really optimize the performance of your code a lot. And I'm now at 7:45, which I think is more than anyone really wants to hear. And so I think I can stop there. I've got some more slides which we can post, but I think we're hitting the point of diminishing returns here. So at this point, I was just to open the floor to questions.
Do we have a microphone? Yeah. Any questions?
So the question was, are you planning on handing out picoseconds? I have no plans to hand out picoseconds. Not right now.
Questions on the last few slides on these optional flags. So these were just flags, whether it can be turned on or off. Like, how is it related to?
They're not able, you can't turn them on or off. This is telling you the flag is actually reading. There's an instruction on x86. It's CPU ID, that's right. And that tells you what circuits are available to do certain instructions on your computer, right? And so basically there's this kind of similar thing on ARM where you say, hey, do you have a circuit for doing 64-bit floating point matrix multiplication? And in this case, like whatever machine I did this on does not have that instruction here. I can't just turn it to 1.
And how to use like one of these existing like instructions that's sort of listed 1 here?
Yeah, so the floating point reciprocal square root was actually one of these instructions. And so, you know, there actually is an interesting kind of question, which is, so first of all, there is this thing called the ARM Developer Guide. Oh, sorry about that, yeah. So there's if you look up the ARM Developer Guide, it will give you, so for instance, you find out something that you might want to use, and then you go to the ARM Developer Guide, and it will give you detailed instructions on what that, how that instruction should be used. Okay, it's not that detailed, and the documentation is not that good, but yeah, you kind of get the point, right? You can go there to this website. You can even download a PDF, which is 25,000 pages long, and you can look up each instruction and try and figure out how to use it. And you know, continuing along that route, I actually was not able to read the ARM Developer Guide before reading other references. There's this book by Curseworm, which is called Programming with 64-Bit ARM Assembly Language. Sorry, not Curseworm. This is Stephen Smith. And Stephen Smith's book is amazing. It's really, really approachable. And so I would start with Stephen Smith's book and then bootstrap to the ARM Developer Guide, because the ARM Developer Guide is just too hard.
Hi. So you mentioned how for like the move instruction, you can put the immediate value in the instruction up to 16 bits. But what if you had a wider value?
Okay, so that's an interesting question. So there's 2 solutions to do that. One is the move instruction actually takes a shift. And so what you can do is you can say, I want to move this 16-bit instruction into the low bits, and then this 16 bits, I'm going to shift it into the higher bits. And so then instead of doing a 32-bit instruction, you would just do 2 move instructions. That's probably not very common. What you generally would do instead is just have a data segment in your code, and then you would just like address that. Yeah, so actually that was in the slides we didn't cover. Let me see if I can show you. So this is actually the slide where they're going to show you how to do addressing. So basically you do this thing called, you have a data segment here, and then you have u@page. So first thing you have to do is you have to find the page that data is in. And then the next thing is you had to add the page offset, and then you're golden. I mean, yeah, that's still 2 instructions. So if you have 64 bits, I guess you just, you know, just do that and do the move thing. So, yeah.
Oh. Yeah. So at the end of the day, we're not assembly programmers, we're C++ programmers. So I'm writing a C++ program and based on this talk, I look at the assembly and I find, oh, it's not using this square root function or, whatever. Like, what should I do? Should I use like intrinsics or write inline assembly? Like, what should the next steps be if I find that it's not using an instruction that I want?
Yeah. So, ultimately, with this talk, I had to kind of scope it to only learning assembly. The way that I would, kind of move forward is definitely try and like find intrinsics, right? But there's also, if you're a compiler writer, there's things that you can do. And also, I've noticed that a lot of like std library code is not that well optimized. There are a lot of low-hanging fruit in just like the GCC libstd C++ that, I personally know of instructions that could be used to make a lot of things better there. Unfortunately, the GCC contribution is too much of a bear for me to handle at this point. But yeah, I mean, you can do, first of all, you can just like link the assembly into your program. If you write an assembly file, you use intrinsics, you can use inline assembly. There's lots of options.
Do you have any of these tricks in Boost Math?
So, ironically, I don't use these tricks in Boost Math, qua math, actually. I actually have a progress bar. It turns out there's an assembler instruction for measuring time elapse that's like super fast. You can get like, you can measure the number of cycles on a counter in like 250 picoseconds. Whereas if you call like std chrono, it's like 50 nanoseconds. So if you want to write a really, really fast progress bar, say for like a matrix reduction or something like that, that's what I do.
So over here, it looked like there was some conventions when it came to function calls, and then you also showed some conventions when it came to system calls.
Yeah.
So how do you learn like the system call conventions? Is that one of those you just hunt and peck and like look online, or is there good references for that? Or like, are there common things between platforms, or is it all really platform depending? Tell us more.
So I can't speak to how platform dependent it is. I do know that there is a header file on the Mac system that identifies all of the syscall numbers and has like code comments which tell you what the number means. So you're like, oh, this is syswrite, and that's 4. Define syswrite 4. And ultimately, I think I kind of struggled with that, right? Like I'm just like basically like digging into like some like bowels of the Mac OS to find these sorts of things. And I don't really know where they're documented any more than that. So regrettably, I have a very good, poor answer for that one.
Yeah, there's a comment online asking, could you comment on the relative performance of GCC and Clang for ARM?
I haven't noticed anything. I mean, since I'm generally like using Apple Silicon, like GCC is just like Clang like all the time. And so I don't have much experience with that. So.
Any other questions? I'm curious about something, which is, how does the debugger work with like an assembly code? Is it replacing the assembly code instructions underneath the hood?
Yeah, I can actually show that. So here's one where like LLDB, let's just do, oh yeah. So here's one. So I'm just going to do LLDB L2 norm, break at main, run. And then here's my assembler code. So I can actually print as hexadecimal x0. And then you can see that the page, this is saying, oh, here's get the page of the data, and the page is 4096 bits. So all 3 hexadecimal bits are 0. I do next instruction, and then it's got the add of the page offset. So I can print as hexadecimal x0 again, and then that gets the page offset there. And then I'm going to move into x1. So before I call this, I have garbage. Now I have 3. And now I'm going to branch and update the link record. So actually, let's print x30, because that's the link record, and it should be, I hope it's garbage. I would be surprised if it's not. Okay, so it at least changed. It might have been garbage. And so then we can just continue. I think that the debugging experience is actually pretty easy. It's not that bad.
All right. Any?
I noticed in the demo that when you broke on main and hit run, it was on the second instruction. Is that just an artifact of the debugger?
I think that is a debug, a bug in LLDB. I actually put in no ops at the first instruction sometimes, just so it would like stop right after the no op. I don't know why that's happening. It may be a bug, or there may be some fundamental thing. No clue.
Okay. Well, everyone, let's give a big thank you to Nick